Well, welcome back, everyone. I hope you got lots of snacks and coffee and juice. So our second speaker, Morris, who is the J. Tuzo Wilson Professor of Geophysics at the University of Toronto. His research involves experiments on emergent patterns in fluid, granular media, ice formations, and fracture. He is also interested in natural patterns and in history of physics. He has sometimes passed off his scientific images as art. He is also interested in patterns in nature and in the history of physics. He's appeared occasionally on the Discovery Channel. Stephen earned a Bachelor of Science and a Master of Science from the University of British Columbia and a PhD from the University of Toronto. He was an postdoctoral fellow at UC Santa Barbara from 1993. In 2003, he won the APUS SAC Teaching Award at the University of Toronto, and in 2004, he was given the U of T Faculty of Arts and Science Teaching Award. Stephen was a senior visiting fellow at the Isaac Newton Institute for Mathematics at Cambridge University in 2005, and a visiting fellow at Clare Hall at Cambridge in 2006. He became a fellow of the American Physical Society in 2012, and in 2014 became the J. Tuzo Wilson Professor of Geophysics at the University of Toronto. And his talk today has something to do with making sound visible, patterns at the confluence of physics and music. Professor Morris.
Yeah. Thank you. Thank you. I'm not sure how much music you're going to hear in this lecture. You can tell me after whether it was musical. The sounds will not be as pure, perhaps, as previous talk. I'm going to tell you about, my purpose here is really to show you a bunch of analog devices which have a long history, and I'm kind of obsessed with the idea that we should do things in the real world in an analog fashion and not do too much electronically. I myself spend all day in front of screens, and so sometimes I just want to shake stuff or hit things, right? So that's what we're going to do today. So I'm going to tell you a kind of shaggy dog story about this theme of making sound visible, and that goes way back in history, and that's basically what I'm going to do. Okay, so sound visible has a very, very long history, this idea that sound might be visible in some circumstances. And the cast of characters is perhaps a little surprising. The first guy is Pythagoras, and Kunt, I will come to his invention in a minute. Chladni is the guy with the shaking plates, and I have a shaking plate here, and this is in fact a picture of a Chladni figure, as it's called, and I'll explain what those are. And rather surprisingly, Napoleon will make a brief visit. And one of the most famous mathematicians of the early 19th century is Sophie Germain, and I'll tell you her happy, sad sort of story. And finally, as we move toward the end of the 19th century, Lord Rayleigh, well, Faraday actually comes before Rayleigh. Faraday are 19th century titans of sound, if you like. Faraday is a titan of many different branches of physics. And finally, I'll talk about a kind of 1960s and 70s phenomenon, this Hans Jenny character who invented a whole new science called Cymatics, which I will discuss. And finally, I will, since we are talking about Steve Reich, I'll put on a brief silent performance, I guess you would call it, of one of Steve Reich's famous pieces. Okay, so the history of sound goes back to this, what I like to call string theory, and the idea of that different vibrating strings have nice relationships to each other if they're in whole numbers. Ratios of frequencies is traditionally ascribed to Pythagoras, of all people. And if you know anything about Pythagoras, you know that he was kind of a numerical mystic who believed that numbers were kind of the basis of all things. And he also famously did not believe in irrational numbers, that is, numbers that are not expressible as the ratio of two integers. And supposedly, Pythagoreans never came to accept irrational numbers, for which they've been vilified for 2,000 years, of course. But Pythagoras it's traditionally ascribed to Pythagoras that if you take two identical strings and or you take the same string and pluck it, and you can get various modes. So this is called the fundamental mode, where the whole string just goes up and down. If you get a higher frequency, you get what's called a node in the middle, a place where the string stands still. And this is what's called a standing wave, where the string does this. And this one has twice the frequency of that one. Okay, so they're in this nice relationship to each other. And then you can get the next mode and the next mode and the next mode and so on. And so here's actually a old woodcut of Pythagoras in kind of medieval dress. Okay, so there are no pictures from the Greek time of Pythagoras. We have no idea. All we know about a name and a few dates. But here he is playing around with a bunch of stretched strings, which are all of length, but they have different weights on them. You see the numbers 9, 12, 16. So the idea is that you can get harmonious relationships between the sounds that the strings make by stretching them with sort of weights with the right ratio of weight on them. And here he is playing around with pipes of different lengths. So here's a pipe of length, here's a pipe of length 16, and how do those sound together? And this one, they're bringing different bells with different sizes or glasses with different amounts of water in them and so on. I'm not sure what they're doing in this picture. I think they have hammers of different masses, and they're bashing a piece of metal with it or something. I don't know. This one's a little mysterious. But the idea is that there is a physical basis to this idea of just intonation, the idea that whole ratios or simple number ratios of frequencies sound nice together, and that is ascribed to Pythagoras. And physically, it's because if you pluck a string or blow a pipe, there is a simple numerical relationship between the frequencies it makes if it has modes which are in simple relationship to each other. So 3 to 2 is, 2 nodes, and the maxima are called antinodes. And you can set into motion the string in these various ways, and you can listen to it, and because of the way your psychology is constructed, you can explain this, but it's a nice sound if they have the right ratio with each other. So it's a little less obvious how this works for sound itself as opposed to the vibration of a string. Inside of a pipe, like an organ pipe here, what we do is we set off a kind of trapped sound wave inside of the pipe, and whether that sound wave, the wavelength of that sound wave fits nicely in the pipe or not is equivalent to whether the wave fits nicely in the length of the string that you plucked. So this is a quarter of a wavelength. I have an open-ended organ pipe, and I have the closed end here, so the sound has 0 amplitude down here and maximum amplitude at the open end. Then a quarter of a wavelength fits into the pipe, and that would be something like the fundamental or a quarter of the fundamental of that pipe. And if I manage to resonate it higher and higher, I'll get higher and higher notes. And the point is that these things have simple frequency relationships to each other, and that's the physical basis of sound in a pipe. Okay, so so you can't see the sound in the pipe unless you do something. What can you do to see the sound in a pipe? And normally sound doesn't have any manifestation in the air, but it turns out there's a very subtle effect. It took a long time for people to realize this, but it turns out that if you trap sound in a pipe and you have a fairly high amplitude of sound in the pipe, there's actually a kind of rectifying effect. That means the frequency of oscillation of the sound gives rise to things at twice that frequency and things at the difference frequency, okay? And the difference frequency is DC. In other words, there's a continuous pressure generated in a pipe which does not oscillate at the sound frequency, but is actually just a steady pressure difference. And that's called acoustic streaming. So if you have a very loud sound in a pipe, it gives rise to tiny little air currents that move inside the pipe. Okay, this is actually similar to the effect where if you take a small, like a cork or something, and you put it on a wave on water, if you have the wave passing this cork, the cork will bob up and down, and it won't make any progress. But there's a tiny little nonlinear effect where it slowly drifts along, okay? So back in the 19th century, people who worked out the physics of sound and the physics of waves realized that there was this tiny leftover effect which could move something. Kundt invented this amazing device, which is nothing but a glass tube like this. And in that glass tube, you put a very, very fine powder, like lycopodium powder, which is the spores of a mushroom. And then if you generate a very loud sound mode in that tube, like an organ pipe, the leftover, the acoustic streaming pressure will move that stuff around in the pipe and pile it up at the nodes and antinodes. It actually piles it up at the antinodes, at the maxima of the sound. So the Kundt is to visualize sound by moving little dust around in a pipe. This is actually a picture from his 1866 paper where you can see the maxima and minima of the sound mode in the pipe. You kind of pile it up and visualize the sound by that mechanism. Okay, but it's important to realize that you're not seeing the sound directly. You're seeing this acoustic flowing effect, which is basically a nonlinear effect caused by this high sound vibration amplitude driving very small secondary flows. Okay, although it took a long time for people to figure out the physics of that. That's basically the physics of it. Now, perhaps the most famous example of using this effect to visualize sound is something called a Rubens flame tube. And a Rubens flame tube was invented way back in 1905. But it did not become famous until YouTube, okay? And I'm not sure why. I mean, I've been in physics for 30-something years, and I never heard of a Rubens flame tube for many, many years. And then a few years ago, somebody resurrected this trick and made a YouTube video about it. And now every kid making a science fair project wants to make a Rubens flame tube. My kid, when to a sort of sciencey high school, and there were like 2 or 3 kids trying to make the Rubens flame tube for a science fair project. Okay? But what I have here is a Rubens flame tube, and I didn't tell the field that we were going to do this, but I'm going to make some fire. Okay, I have a little bottle of propane. And the idea is we're going to generate pressures in this tube. We're going to generate pressures in this tube, and it's connected to a keyboard back here. It's all right. The demonstration will be over before they catch us. I also have a fire extinguisher in case something goes wrong. I hear it. Come on, baby. There we go. Okay, we need less than that. So the idea is, there we go. So there we go. So what's happening is that propane is flowing into the tube, and it's just coming out the jets. And the jets are very, very sensitive to the pressure, the mean pressure behind them. So if I play a note, I don't have much sustain on here. But you can see that there's different numbers of maxima in the shape of it if it comes close to this resonance of the tube. This one, I think, that's pretty good. There's an electric piano back here. So I'm cheating a bit and using electronic. This is a speaker at that end, and it's driving a sound mode inside the tube. So you see the maximum. There's a node right there. And there's a maximum here, and a node there, and a maximum there, and a maximum there. So now we need someone who can play a short tune on the piano. Midori was going to do this, but she's not here.
Doing the scale.
Okay. What we need is, don't touch the plate. Okay, I'll turn the flames and the fire extinguisher. Wait a minute. I've gone out here. Okay, hold on. We haven't run out of gas. I just turned it down for a second. Okay, go. There you can see many maxima, and down an octave lower, you can see less. Okay, so thus the Rubens flame tube. Now, in case it didn't work, I have a picture. It's over. I'm going to turn the propane now. In our department, this is called the barbecue. We refer to it as the barbecue. And we're allowed to put it in any room in the university, provided we have our fire extinguisher handy.
Yeah, this would be the next
Different Reuben. Okay, so in case it didn't work, I have this nice picture, but This is basically what you see. Wherever there's a maxima in this acoustic tubing pressure, you get more gas out, and that gives you a bigger flame. Okay, so that's a 1905 trick for visualizing sound. But the king of visualizing sound is definitely Ernst Chladni. Chladni is sometimes called the father of modern acoustics, and he lived at the end of the 18th century and the beginning of the 19th century. And he actually rediscovered some things that had been known before, but he discovered, for example, that you can visualize the motion of a plate by sprinkling sand on it. And this was actually discovered first by Robert Hooke, who was a contemporary of Newton. And if you know anything about Newton, he spent most of his life trying to eradicate Robert Hooke's reputation after Hooke died. So for some reason, Hooke kind of forgotten in the history of sound, even though he had some very important ideas about it. But anyway, the idea was rediscovered by Chladni, and he wrote a book called Die Akustik, which is sort of the foundational book of scientific acoustics. And I think of Chladni as kind of the man at the branch point. He's the kind of threshold when physics and music were both the same thing. The same people did both things. But about post-Chladni, the two bifurcate from each other. And music people go one way and kind of scientific people go the other way. And they have not come back together very efficiently ever since. So what he invented was, he invented lots of things, but what he invented was a thing called, now we call it a Chladni plate. And this very simple idea is you have a very powerful shaker. In this case, it's a big speaker sitting on the floor here. And then you put a plate of some shape on it, and I'm going to put a square plate on there. And then you shake the plate at different frequencies. Now, what Chladni did was he used glass plates usually, and he bowed it with a violin bow. But that's hard. Okay, it requires skill. So what we do is we drive it with a modern signal generator and a power amplifier. And when the plate is well connected to the speaker, which it is currently by an emergency bit of double-sided tape, it will resonate the plate. And then the key thing is I'm going to sprinkle sand on the plate. And as the plate vibrates, there are places where the plate is doing this, okay? And there's a line there. Unlike a string has a single point where a node occurs, vibrating plate, the nodes are lines. And wherever the sand is on the plate, it will tend to be chucked up in the air, and it will tend to pop up the node lines. So the node lines, the lines you're going to see, visualize the place where the plates are doing this, that line. Okay, I didn't tell them I was going to make a mess either. So what I'm going to do is, what I've got is a projector here, which is showing the plate, hopefully, yes. And you can see the whole, it's actually square, but the fisheye of the lens makes it a little not square. The trick to it is not to put too much sand on the plate. And hopefully it won't fly off the driver. So we'll start at a low frequency first. And I've got a little cheat sheet here. So you hear it getting louder. I'm approaching a resonance. Okay, here's a resonance. Now the trick is to give it a blast or at the resonance. Can you see it? Yes. Okay, so that's a fairly low note. If then I have a very special tool called a musser. And we use this to muss up the sand. Now we'll try a higher note. 142, that's very low. We'll try a lower one. I'm a little worried that it's going to come apart, so I'm going to try a lower one first. You could be the musser. Let's put a bit more on. So this thing is called a Chladni figure after it's made. Okay, let's go for a high one and maybe break it. 384. Now, unfortunately, unlike a vibrating string, the modes of a plate aren't in a nice progression of frequencies necessarily. And so the frequencies don't have any particular, they have relationship to each other, but it's not particularly musical relationship to each other. Chladni did invent a musical instrument on vibrating plates. It was kind of a keyboard which put a little kind of rubber on the side of a rotating disc and produced a sound. And then I guess you use differently tuned plates. I'm not sure. Okay, we're going to get real high here. There's a higher one. That's nice, eh? It's interesting that you might say, why do these things avoid each other like that? Well, if you were to calculate the exact modes of a perfectly symmetric plate, then those two node lines would cross each other there, okay? And so that means that point where the two node lines cross is a point of very high symmetry. It's only going to be there if the plate's perfectly square and the driver is perfectly in the center. And there's no sand on it because the sand actually loads the plate a little bit. But any tiny little breaking of symmetry of the plate causes what's called an avoided crossing, so the two node lines will pull apart from each other. So these little places are kind of a measure of how perfect the plate is. We're going up. We'll go to 689. This is going to be a little painful. I'm sorry for the delicate musical ears in the audience. Okay? That's pretty good, eh? So that's not exactly twice the frequency of the previous one. It's some funny number, not obvious. Shall we try for a really high one? It's going to break for sure. More uniformly. So,
Very good.
yeah, because it's more delicate when it's high. Well, you want the sand to be a little more. You can just put more on. Okay? Ready? Okay, ready? There we go. Okay, so that's, I'm not going to do another one. So that's a Chladni plate. What Chladni did was he did not know, he knew the plate was vibrating, but he had no way to calculate, no way to understand the mode of the plate, because at this point, some of these things had not been worked out. But he was able to map, using both glass plates, different shapes, all sorts of different modes of the plates, and he made a big sort of catalog, and this appears in his book, The Theory of Diacoustic, in 1802. And I've managed to make high Chladni figures over time. These are, you saw, this one we have here is sort of in that neighborhood of frequency, maybe that one. It might even be that one, actually. But as you drive the plate harder, it takes a longer time, and you have to endure more terrible noises before you can hear it, but you can actually drive the plate to very, very high modes using a powerful shaker. So this is the kind of sequence of Chladni figures made, starting from lower and higher notes. This one is interesting, by the way, but you see that there's a kind of double pattern here. There's a kind of checkerboard, but there's a secondary pattern which is on a bigger scale. Two modes that are close to each other, which are interfering with each other because they have almost the same symmetry. So there's a lot of physics in Chladni plates. You can also, of course, do it in different shapes. It's interesting you do what's called a stadium shape, and I won't go into why that particularly. But also, traditionally, violin makers have used Chladni motions to diagnose the vibration modes of pieces of wood that they're making their violins out of. So I had a very large aluminum plate made in the shape of a violin, and you can shake that and get interesting modes out of that. Chladni is a kind of a hero because he not only did all this interesting stuff, he went out and demonstrated it for the public. He went on tour, basically, and he traveled all over Europe giving kind of magic shows in which he pulled off these Chladni figures for everyone to see. And this is him demonstrating, his technique for all the sort of ladies of some salon. So this is what we're having right now, is a kind of salon, right? This is the idea that scientific and artistic endeavors can be simultaneous in both the case, and also that you can do them in a kind of nice setting where you wear a tailcoat and show them to intellectual people of all kinds. Okay, now it brings Napoleon. Napoleon was himself rather interested in science and mathematics, although he wasn't very good at it. He was kind of a wannabe, kind of, the way politicians are sometimes. Chladni was a German, but he eventually, his work was eventually brought to the attention of Napoleon, and he had an audience with Napoleon. I think there's a picture of him showing Napoleon. So he demonstrated his plates for Napoleon on February 7, 1809, and Napoleon was so impressed that he established a prize for the mathematical explanation of Chladni figures. And being Napoleon, it had to be a big prize, okay? So it was some thousands of francs, equivalent to 1 gram of gold. So Napoleon directed the French Academy to institute this prize, and he funded the prize. He also funded Chladni to publish a French version of Diacoustique, and he dedicated it to Napoleon in 1809. Now, what's interesting about this is at the time of this prize, no known physics of vibrating membranes like this. It was decades before the physics was worked out. But one of the first people, in fact, the only person to attempt this difficult mathematical test was this Monsieur Blanc, which is the pseudonym of Sophie Germain, the famous female mathematician of the 19th century. She was not allowed to be a member of any academy. She was not allowed to go to any academy meetings. During the Revolution, she read books in her father's library and taught herself mathematics. And her parents tried to, deprive her of these books, but eventually they gave in and let her study mathematics, and she became extremely good at it. And she's famous particularly for the Chladni plates, but also she worked on Fermat's last theorem, which is certain algebra, and theory of prime numbers. But in order to enter the mathematical world, she took the name of a deceased member of the French Academy named Monsieur Leblanc, which is like the Mr. Jones or whatever of the French Academy. And she entered the prize in 1811 and 1813. And the jury, whether they were aware that she was a woman or not, I'm not sure, but anyway, she didn't win. She also corresponded with the famous mathematicians of the day, and she eventually revealed herself to them in correspondence. Finally, in 1815, her effort, about 10 years of effort to explain the shape of Chladni figures, was judged to have been a success. And so she won the prize, but because she wasn't allowed to go into the French Academy, she never arrived to collect it. And she died somewhat after that, not too much after that. Okay, so it's a tragic story, okay, but a famous story. Eventually, the problem was solved, and I want to show you what the solution looks like, but it took until a book on the theory of sound to completely solve the problem. The problem is that a drum head, like a stretchy membrane, it obeys what's called a second-order equation, which, the vibration of the drum head, the returning force of the drum head is caused by the stretching of the drum head. So it's quite similar to the stretched string. And so it makes a simpler problem, a simpler equation. And the hard part of the problem is to conditions. That is to say, how the ends of the string determine the motion or constrain the motion. And in a stretched string or a drum head, constraints are physically obvious. You clamp the ends of the string, you clamp the edge of the drum head, and you know how the equations work there. Okay. The problem with the vibrating plate is the edge in this plate is free. Okay. And it turns out that the plate requires a fourth-order equation, and that means 4 boundary conditions. The first 2 are simple, but the other 2 are not so simple. And so Sophie Germain did not get the 4th boundary condition correct. And it wasn't until later in the 19th century that people figured out this rather complex mathematics. And Lord Rayleigh was the quintessential English scientist. He had a county seat where he had a laboratory of his own, and he did all of his research because he wanted to. He was the Lord, right? Eventually, he was given a prestigious position at Cambridge, so he's the only person ever to be the Cavendish Professor of Cambridge and a Lord at the same time. And so he eventually wrote a large book called The Theory of Sound, which came out in 1877. And the story is that he wrote the book while on a Nile cruise because he had some kind of respiratory problem, and his doctor told him he had to go to Egypt. So to keep himself busy on the Nile cruise, he wrote this large treatise on the theory of sound. And he worked out in some detail the theory of Chladni plates, and this, I would say, is kind of mathematically the end of the story. We now know how to calculate the Chladni figures. And just to show you what this looks like, here is chapter 10, the vibration of plates. And he starts out by writing down a potential energy. So if I flex the plate in an arbitrary shape, how much energy do I have to put in that? And then he uses various to calculate from the flexing of the plate, the energy flexing of the plate. So this is a fairly sophisticated thing. And right about here, he works out the boundary conditions. Now you see there's a crucial difference between Chladni and Napoleon and musical acoustics in the beginning of the 19th century and Rayleigh and acoustics at the end of the 19th century, which is, unless you know advanced calculus, you can't follow this thing. There are some pictures in text, okay? So here, finally, after a lot of work, he gets equations which he solved numerically, which, by the way, in the late 19th century meant pencil and paper and a lot of grunt work. He can actually solve for the things and find the modes of square plates and draw them. And this is one here. Now, look a little different from the figures that I've been showing you because this plate is free. That is to say that it is not driven by a point in the center. This plate has actually got a bolt in the center that goes to the driver. So that puts another boundary condition on there, which is not in his equations, but we could put that into our equations if we wanted to. So around this point, I can say that the sort of classical theory of Chladni figures has been worked out. But I think what happened is somewhere between Chladni and Helmholtz and Rayleigh, the musicians got left behind or went off on a different branch of the tree, and the two sides don't understand each other anymore, okay? Which I think is too bad. You don't really have to do all this mathematics to appreciate that this is a beautiful pattern. Okay, I want to say a little bit more about patterns on shaking things. If you take a Chladni plate like this, and instead of having sand on there, you put a very, very fine powder on, like the lycopodium powder we talked about before, then something weird happens. The lycopodium powder does not go to the nodes the way you might expect. It actually goes to the antinodes. And that is, again, Kuntz's observation. It turns out that above the plate in air, there's a vibrating sound field and little pressures that push things around, and it turns out that the stuff goes to the antinodes. And this was very confusing to people, especially Faraday in the 19th century. So Faraday engaged and he had an air pump. He put a plate in a bell jar and proceeded to demonstrate that when you pump the air out with this hand-driven air pump, that the lycopodium powder went to the nodes, just like sand does. When you let the air back in, the sand goes to the nodes, and lycopodium powder, which is finer than the sand, goes to the antinodes. So he worked out this mystery of how the Chladni plate motion worked and how it depended on the air and for different sizes of stuff. And in the process of shaking that plate, he shook everything. This is how Faraday did work, right? But I've got this and I've got this. Let's smack them together and see how things happen. He would write it all carefully in his notebook. He shook plates covered with liquid, particularly water, blood, egg white, turpentine, any liquid he could get his hands on, basically. And he observed another phenomenon, which is now called the Faraday instability, which is surface waves on the surface of the water sitting on top of a vibrating plate. And this turned out to be far more interesting than the thing he started out to study. And he actually wrote a huge appendix to his paper of 1831, which is now the definitive study of what are now called Faraday waves. Okay? So what is a Faraday wave? You've all seen a Faraday wave. If you take a styrofoam cup, it's not a styrofoam cup, but if you have a styrofoam cup and you put your coffee in it and you pull it toward you across the table, you can sometimes get stick-slip motion where it buzzes, right? Everybody seen this? If you look at the surface of the coffee, if you get it buzzing just off, you'll see the surface of the coffee is very suddenly covered with little waves. How many people have seen this? Excellent. Those are Faraday waves. The crucial feature of them is that they don't appear at acceleration. They appear when you pass through a critical acceleration. So if you start with a plate covered with liquid, you begin to shake it up and down, and you increase the acceleration, it stays flat, and then rather suddenly the waves appear. Okay? So this is instability. It turns out that surface wave that's bouncing around on the surface of a liquid is driven or pumped by the shaking motion. Okay. Another little odd fact is, which tells you they're nonlinear waves. It turns out that they oscillate up and down at half the frequency of the driving force. Okay, so they're not proportional to the driving force. They come in at half frequency. Okay, and Faraday realized this, and he realized that they had nothing to do with the modes of the plate. In fact, most Faraday experiments use a big stiff plate, so the modes of the plate are not relevant. So this is a thin plate, so it flaps. But if you use a thick plate, then you can get Faraday waves when you shake it. Okay, so I have a little gallery of Faraday wave pictures. Now, it's interesting. It depends on the viscosity of the liquid and how deep it is. If you have rather viscous liquid like oil, you get straight waves. So this is looking at the reflection of the surface. So as you shake the plate, the waves kind of do this, and they're long and straight, just like ocean waves. Okay. If you reduce the viscosity a little bit, it turns out that a wave in this direction is unstable to a wave perpendicular to it. So a square pattern of waves appears. If you of the stuff or lower the frequency, you can get foam patterns of waves. Okay? All these things are surface waves that are nonlinear, and they're interacting with each other and driving waves at different angles to themselves. It has nothing to do with the shape of the plate. So think of a direct sound effect. The plate is vibrating up and down at some kind of frequency, and the fluid is responding at half that frequency in a complex fashion. And this is actually a very interesting subject of nonlinear physics, and we have an undergraduate lab in the north here of our program where the students do this experiment and try out all the different viscosities and all that. It's something interesting happens if you try what's called a complex fluid. The fluids like, for example, oil, they're viscous, but they're Newtonian. That is to say, their viscosity is independent of how much you shear them. But if you have kids and you know about cornstarch, or oobleck, as it's sometimes called, you can make a mixture of cornstarch and water, and it has strange properties, right? It acts rubbery, you can bounce it like a ball, it flows strangely. If you shake a complex fluid, then something really cool will happen. And this is another one of these YouTube memes. In fact, it's appeared on the Big Bang Theory. That tells you how famous it is. You know, what's the girl comes in and finds the guys shaking cornstarch on the speakers in their dorm room. But the first person in the physics community to work on this was a friend of mine named Robert Deegan, and he wrote it up in 2004. And this is his movie, which he made for the Division of Fluid Dynamics meeting in 2004, and it shows what happens when you shake cornstarch on a speaker. Wait for it. I think it's playing. Yes? Come on. There we go. So that's to see how liquidy it is when you stir it with a stick. Not very dense cornstarch solution. And now when you begin to shake it, wait for it. It's narrated, but I turned off the narration. Okay, you begin to shake it. Nothing happens until you reach 30 Gs at 120 hertz, and that gives you Faraday waves, which look like this. Wait for it. Dong. Now the Faraday waves seem to be shifting in and out. That's stroboscopic effect with the camera. Now we knew about that because that's just Faraday waves. Now an interesting thing happens. He brings in a little pipe with air coming out of it. Wait for it. And he makes a little puff hole. He makes a little puff and drives a little hole in the fluid. And the funny thing is that the hole doesn't close, okay? The shaking makes the perimeter of the hole kind of stiff, so it doesn't close up anymore. And in fact, it has a characteristic size. If you make a big hole, it shrinks down to the small hole, but it doesn't close. So this is not what a normal fluid would do. Okay, so we talked a little bit. The hole actually penetrates the full depth. The black bottom of the plate is visible. And so this is something called a coherent structure. That is a structure which is driven by non-equilibrium forcing effects, which appears, to be coherent and not obvious in the driving forces. Okay, here's two holes interacting with each other, and here's a secondary hole. And these two holes kind of snap up to each other and make a little kind of dance. Okay? So now you can think, well, what is the physics of little holes and shaking, fluid? And now this is the one you've all been waiting for. If you drive the thing harder, the hole is stable, and it makes a kind of finger, and the finger flops over, and the finger flops off another hole, and the whole thing begins to writhe around. So this is, in YouTube, this is called the cornstarch monster. And I think you'll agree that it looks kind of icky and lifelike. Can't see is that this thing is blurry because it's shaking up and down at 120 hertz. But the fingers aren't moving approximately DC, and they're setting off each other, and fingers set off neighboring fingers until you turn off the shake, and then it abruptly falls down. So it's called a dissipative structure. Okay, so how many people look at the cornstarch monster on TV or somewhere, right? Okay, so when Robert Deegan discovered this, he thought that he was the first person to see this, and it wasn't until YouTube days when everybody started messing with like Rubens flame tube. But meanwhile, in another part of the forest, there was this guy named Hans Jenny, I'm not sure how you pronounce it. He was a Swiss-trained medical doctor who late in his life became obsessed with shaking things. That's all you can say. He was a follower of Rudolf Steiner and a theosophist. Okay, so he believed in a world behind the one that we see here, which is animated by some unseen forces in some way. And he believed that he could see insight into that world by looking at the shapes of things that he was shaking. And to his credit, he didn't sit in an armchair and think about this. He actually did it. He actually took a signal generator, the beautiful old signal generator, and a spinner, and he shook Chladni plates. And I believe he was aware of Chladni, but he didn't really understand the physics of Chladni plates. He just knew that they were compelling to look at. And also shook every fluid and grain that he could put on a plate in thick layers. And the most important thing he did was he took excellent photographs of all these things. And so he published in the 1970s 2 books of photographs of what happens when you shake stuff. And they're very striking pictures. Here is a pile of a light granular material like flour, and every heap it actually entrains air, makes a kind of flowing pile that does this. Faraday had already investigated this in the 1840s, but it had been completely forgotten to the world. Okay, but Jenny pulled it out again and started working on it. You can do all sorts of coherent structures of heaping sand. So these little fingers are sand that's sort of streaming up and down these piles, driven by air. He also rediscovered, without knowing what they were, Faraday waves. Okay, so here's a beautiful square pattern taken by Jenny, and here he actually invented something where he shines the light upward through the fluid and projects it onto the wall, and so you can see a kind of focus pattern of the square pattern of Faraday waves. And then if you take a small droplet and you shake the droplet, you can get very beautiful symmetry in the modes of the drop. And you can see a six-fold symmetry. This is actually a threefold symmetry which is oscillating between the 2 threefold shapes. And this one is probably his most famous picture. It's what it is, 8-fold symmetric pattern in a shaking drop. And he invented a science of this stuff, which he called Cymatics. And it's kind of ironic, because over on one side of the world, where all these physicists were working their way through quantum mechanics and all this stuff, and they finally got back to thinking about Faraday waves and granular materials and shaking nonlinear patterns around about the late 1970s and early 80s. But unbeknownst to them, unbeknownst to anybody in the physics world, there was this Hans Jenny guy coming up the other branch of the tree doing all these beautiful experiments, but interpreting them in a completely a kind of Goethe holistic theosophical sort of way, and publishing beautiful pictures of it. So many years ago, I had an electrical problem in my lab, and the university called an electrician. An electrician came in, and he started to fix the electrical problem. He noticed I had pictures of Faraday patterns on the wall. He said, "Oh, you know about cymatics." And I said, "What?" And it turned out that he was an artist when he wasn't doing his electrical work, and all artists had this book and had heard of this book. How many people have heard of this book? Oh, but so in the art world, people have seen these pictures and they're known. In the physics world, nothing, okay? So the 2 branches just were going along independent of each other and they never came back together again. So it turns out, of course, that Jenny also shook cornstarch way back in the 70s, and he wrote all about it. He had all these beautiful pictures of the cornstarch monsters. Here's a very similar cornstarch monster that was just published, decades earlier. Okay, so I think this is a kind of parable. It shows that we scientists have fallen down in some way. We We didn't explain, we didn't get this stuff out. Even though this is classic stuff, it's just Jenny had to discover it over again and come up with a whole new theory of it, independently apparently, and it's a kind of parallel track. So it shows that it's an interesting problem that people come back to it on parallel tracks. Now, cymatics, I don't think you could call Jenny a wave kind of guy, age kind of guy, but it unfortunately, depending on how you look at it, has been kind of taken up in more recent times by people with much more mystical agendas than Jenny had, and they want to use vibrations to explain, the music of the spheres and the magic of the universe. So if you Google cymatics, you'll discover all sorts of new agey stuff, and in particular, they want to use the vibration, the idea of some hidden music is organizing patterns in the natural world. And so this is a famous example. This is a tortoise, which has a kind of segmented shell, and you're supposed to imagine that some unheard vibration in the growth of the tortoise, which is somehow producing this pattern, which is analogous to the pattern you see on a shaken plate.
That's not true.
Okay? The shaken plate is actually physically different than, and I can explain this too. The explanation is not the same. The only thing that's between them is the deep mathematics of the symmetry of that shape and what kind of patterns tessellate that shape. So at some very abstract mathematical level they're the same, but down at the level of vibrations and physics they're not the same, or at least that would be the scientific answer to this. That doesn't prevent people from kind of appreciating the beautiful symmetry of these patterns and this beautiful symmetry of this pattern in the same kind of way. Okay, I'm coming to the end. I couldn't talk about the physics of vibration without coming back to the pendulum, okay? So this is Steve Reich, this pendulum array musical piece, and the idea is that you have an array of pendulums which are microphones, and below them you have speakers, and you let the microphones go, and as they pass in the vicinity of the speaker, there's feedback, which is a nonlinear effect, and there's a little squawk of sound, and then as they swing back and forth, it makes this kind of sequence of squawks of sound. Now, as far as I know, he didn't choose the lengths of the pendulums carefully. Does anyone know?
I think it's practical.
Just practical, okay. So they all have approximately the same length, and they go in and out of phase with each other. But what I have here is actually a tuned pendulum array, which I'm going to poke up here. We know that the period of a pendulum depends on the square root of the length of the string. Actually doesn't depend on the mass of the pendulum, although these are all the same. So what I did here was I made a sequence of pendulums. And the frequency of this one is in a whole number ratio to the frequency of that one, and that number is about 50 to 51, I think is what it is, okay? So for every 50 swings of this one will swing 51. So after 50 swings of this one should line up with it again, okay? And then each pendulum in between is selected to have another simple ratio. So it's like 50, 51, 52, 53, 54, 55, okay? So what should happen is if I start them all together, they should each do their own thing until some large number of swings later when they should all line up again, okay? So it's actually tuned. And Lillian, who was here fixing the plate earlier, very carefully timed them all to tune them. And the trick is to start them all at the same time using this rod. So you see they swing together at first, and then this swings a little faster because it's shorter. And I oriented it that way so you can look at it from the end. So clearly we should do this with the speakers under it and listen to what it sounds like. Okay, so about here you get an interesting effect where they're kind of out of phase with each other like this. Every second one is out of phase. And then they fall back into phase again. We current. Okay, so now it's 3 and 4. There we go. I think it's set up for takes 2 minutes to come back. So this is called the recurrence of oscillators. If they ever at least come in multiple number of their oscillations, they should recur. Okay, wait for it. Okay, coming. It'll only stay for a moment, of course, and then it'll go back out of phase again. There, somewhere there. Okay, now it's going to fall out of phase again. Okay. So now we need to put the speakers under there and get the feedback going and all that. Okay, so I hope I've convinced you that there's lots of beautiful things to be seen in classical physics and colliding sound with mechanical stuff, and thanks very much for your attention. Yes. Yeah, we should now we do our Salon thing. It only depends on the length of the string. The period only depends on the gravity and the length of the string. So we carefully change the tuning by just changing the length of the string. And in practice, what we do is we time it, and then we turn the screw up here and shorten so each pendulum has a little sliding. We can change the tuning. And if this one is 1, this one's 11, this is 1 time, this is, say, 10 times some period, 11, 12, 13, 14, 15, 16 times that period. And then you pick the period, recurrence time is a convenient number like a minute or 2 minutes. And then Bob's your uncle. Okay? So you see they make a sort of a line. That line actually goes like the square root. It's not a straight line. It's actually a little curve because of the square root length. So yes, well, time for questions for everybody. Yeah.
Vibrating in 2 pitches at once,
Yes. In principle, you should see the superposition of the 2 modes. In practice, you probably don't, because the plate's not really linear. The equation that we solve is linear, and that's just an approximation. Okay. The assumption of the equation is essentially that the amplitude of shaking is infinitely small, but that's not actually true. So when you do the Chladni plate with a pure note, if there's a nearby mode, you'll often see the thing move back and forth between the nearby modes. And because the plate is square, any symmetric Chladni pattern uses the symmetry. If I lift that symmetry by maybe moving the post a little bit to one side, then I will get a lift, so the 2 modes will have slightly different frequencies, right? And so what you'll see is a kind of beating between the 2 modes, and the sand will move back and forth between 2 nearby patterns, which kind of interfere with each other. So if I were to shake it with 2 frequencies which both corresponded to modes of the plate, in principle I would see the superposition of the 2 patterns, but in practice one would win and the other would win, and it'd be complicated. Yeah. Yeah.
Chladni patterns seem to show up in a lot of art forms, like carving with wood and textile printing and things like that. So I'm just wondering if you can speak to any of the influences that might have, like in cultures maybe where like they're not going to have plates where this stuff's happening, but it's the sand. If there's cultures where there's a lot of sand and that kind of stuff is around, like how would people?
Well, I once gave a talk with a person who was interested in Islamic mosaic patterns. And they do indeed look like Chladni patterns. And I think the answer to the question is if you take a square and you tessellate it with a nice symmetry, there's only so many ways you can do it. And they all look a bit like Chladni patterns, because the Chladni figures basically explore all the symmetries. That's the mathematics of it. As you go up in frequency, you're going to hit all the possible patterns which are consistent with that symmetry. And so if you're constrained by a square shape and you want to preserve certain symmetries, it's almost inevitable that you'll cook up the similar pattern.
You don't think it's something that would just occur naturally that people would see be influenced by?
Well, unless they've seen a Chladni figure, I suppose maybe they've seen a Chladni figure. But even if you've never seen one, yeah. Yeah.
Large frozen lake can look like on certain days when there's probably snow. And that, well, of course, there can't really be a relationship, between these 2 things.
Well, there is a.
Like the wind effect, it can make sand be like that too.
Yeah. I mean, at some high mathematical level, these things all kind of come together.
That's why we see these patterns on carvings or didgeridoos and whatnot, because we do see stuff like this.
Yes, they speak to our sense of symmetry. And every time you see one in nature, it catches your eye. If I made this thing and it made a random bunch of lines on the plate, nobody would remember it and it wouldn't be striking. But the fact that these things are all in a symmetric pattern, it's like, if I draw two dots in a line, you see a face, right? If I make a beautiful symmetric pattern, your eye goes ding. And so I think that's the answer. We like them because our brains are wired to look for symmetries and patterns in nature, and when we have a chance to make such a pattern, we make one. And it obeys some of the same rules as cladni figures do, so they look similar. I was going to tell a funny story. There's a church or a chapel somewhere in Scotland which has some stone carvings, which are sort of abstractions, little squares with lines on them, and people have suggested that those are cladni figures. But the chapel is hundreds of years too old for that to be true. So there's a kind of, and they really do look like cladni figures. They have, this kind of shape and circles in the middle and all that. And so they're completely independently discovered, I think. Yeah. The guy at the back there.
Yeah, and actually just a comment before my question. I mean, we were talking about how what we see on the screen now almost resembles the CBC logo. And just this
I didn't think of that one.
notion of recognizing patterns.
Yeah.
Interested when you're talking about science and art diverging, and if you have a thought, maybe going deeper on why you think it's important that the two fields interact a little bit more with each other, because it's apparent that there's two different ways of thinking about some of the things. People come to the same conclusions or similar conclusions.
Well, I have a personal answer to that question. My personal answer is that after many years of doing physics, I finally realized what it is that motivates me to do this stuff. And it's not traditional physics. It's because I like the look of these things, and they do something for me, right? I like making cladni figures, just because I think they're beautiful to make, and I happen to like the way the physics works too, but there's something compelling about them to everybody. And that's basically why I think that physicists should get back into this stuff, because it's out there speaking to us, right? And so I've been spending a lot of time looking at patterns for many years, and I finally realized that what really turns my crank is just the visual and tactile experience of making them. It's like a magic trick, except nature does the magic, and that makes it compelling in some way. And physicists today often study things they can't see, they can't feel, they can't touch. A quantum experiment at the bottom of a tank, you can't, there's no tactile feed, it all comes up on the computer screen, basically. And I don't like that. I'm not motivated by that. I like this. So that's my motivation. And I think that's true of a lot of people. Yeah.
I've seen the cladni plate before, it's really cool. I've never seen the three-dimensional cladni plate, I guess, which is
like a cube.
Movement of some particles in a box.
Well,
with some sound waves.
You could mathematically do that. Physically, the reason this sand works is it just doesn't work in 3 dimensions, but
you could use the spore powder, which is lighter.
I guess I could, in zero gravity, make a box with air in it and put some light powder floating around in it and produce a mode and have it go to the antinodes in the box. Yeah, that would work.
Maybe technically that's really hard to do.
It's technically hard, yes. But it's not physically impossible.
The levitation of particles inside a box is not done in zero gravity, is it?
Well, in theory you can do it with a really strong sound field, but that would be harder even. I should say that every solid, like the bars of a xylophone or anything, if you could see the modes, they would look like twisting modes and flexing modes and bending modes and all these things. And even the whole Earth actually executes modes like that after big earthquakes. And seismologists can actually understand the inside of the Earth by inverting the information they get from the sort of ringing modes of the Earth. So you actually had a picture of a bell. He had a picture of a bell. It was on the cover of the book. Yeah, that's visualized using an optical interferometric. Because you put a laser and you shine a laser on the bell, and whenever the bell is moving, it kind of makes a pattern in the laser light. So yeah, there's patterns in every kind of vibration. It's just difficult to visualize them directly. And so a three-dimensional object like a xylophone key or whatever you call it, a bar, if you could see it, would have internal nodes and antinodes and everything. Yeah.
Another question, Tom. If you like patterns on membranes, and like you said, speaks to you, the eardrum's a very good problem.
Aha, yes. Because it has a little thing touching the center of it, doesn't it? So that changes it.
And actually it doesn't change the patterns on the...
Okay, I think that's probably a drum head as opposed to a plate. Oh, because it's...
They use the word discordant because it has a lot of high order modes.
Yeah.
All past nature with the middle.
Yeah.
Just a question with regard to the pendulum. So to first order, approximately all those things are uncoupled.
That's...
But in reality, they're very weak.
Yes, that's correct.
Kind of start to affect their dynamics.
Well, if I let it swing for hours, yes, they would synchronize. Or the trouble is they can't really synchronize because they have different natural frequencies. If you take two pendulums of the same frequency and you just set them off with random phases to each other, they'll lock together. And they'll lock together because they talk to each other through the bar that they're connected to a little tiny bit. And that's called pendulum synchronization. It was discovered by Huygens in the 17th century. And it's a huge subject, okay? I was going to talk about it tomorrow at my talk tomorrow, but I dropped that part of the talk. So yeah, synchronization of weakly coupled oscillators is a big field, actually. But I think these ones are, over one recurrence time, are insufficiently coupled to do anything. Yeah.
So with respect to the comment, a question about three-dimensional visualization of sound, there's this technique called sonic visualization.
Yeah. Yeah, I know exactly what you mean, yeah.
And also the picture of Pythagoras, the first one with the bard.
Yeah.
He was walking by a blacksmith.
Okay. And the ringing of the...
Between the pitch and the rods.
Okay.
I want to ask you both a question that sort of harmonizes what you're...
Good.
With the visual representation of sound, there's this very clear, simple symmetry with respect to all the possible messy, fuzzy in-between points. And in the just intonation system, the symmetry and simplicity and perfection of those ratios actually shows up as something that's so simple that it almost seems unpleasant. So there's something interesting about how this visual simplicity draws our attention, whereas the acoustic complexity of the tempered systems lends a certain kind of pleasantness to those orders. But I was wondering, actually, Gary, if you would maybe speak to the way that culture filters, to what extent culture and psychoacoustics and physiology affects our appreciation of different systems of organizing pitch, because I was surprised how unpleasant the just intonation system is when you're just doing the ratios, because there's no even, there's no pleasantness, and it's that complexity and the temporal complexity that vibrates in them.
Yeah, we all have different experiences. The psychoacoustics of listening to music is really important. And Steve Reich, actually, you know what I'm saying? Steve Reich is very much aware of that aspect of his music, that we all have a different experience of his music, including the performers. So depending on the hall, depending on your hearing, your own personal hearing loss and all that, we do have that different experience. He's very much attracted to early music where the singers didn't use a vibrato. And when you don't use a vibrato and you're singing in just intonation, you could really lock into these intervals that sounds like you find boring, where Steve just loves it. And his music is more connected to that than opera or any other modern vocal style. He also, Lou Harrison once told me, I know Paul McCartney told me never to drop names, but I'm going to say this, that Lou Harrison said that Steve Reich's music, because of the intervals he used, the simple intervals he used, was much more associated with just intonation than equal temperament, even though Steve had no interest whatsoever in any other temperaments or any other systems of tuning, other than the ability for everybody in the world to play his music on instruments that are standardized. So I don't know if that even gets near an answer to your question, but those are the things that made that I thought of when you were talking about it.
Yeah, I mean, I guess I was just I'm so curious that certain modes or seem really distant between one culture and another, and there might be different justifications. But if you were to justify the beauty, quote unquote, of a system of information based on its simplicity, like you would in visual figures, you'd expect that it would be really mathematically sound, even if that doesn't transpose between keys and stuff like that. But those are systems that sound like alien to Western ears that are trained to hear well-tempered intonations as consonant, even though they're not like mathematically pure. They're not mathematically pure. So I guess this is stuff I should work on the more humanity side of things, and I'm curious about how that weird distinction between purity and mathematical consonants that is playing out in the visual figures and the scales that are mathematically sound versus other scales that are building from a cultural perspective. I guess that's
Yeah, please, Russell.
So there's a little bit of work in rhythm theory, like Charles Kyle, Siegenfeld, they call these groups, they talk about participatory. So basically, the interest in music with a groove has to do with the irregularity, not the exactness of beats or people coming together, but the slight irregularity is the attractive and makes for what we would call music. So
I think that's true of patterns too. The key difference between mathematically perfect patterns and physically generated patterns is defects and slight imperfections. And so you can look at a pattern and you see that it's a natural pattern just intuitively because it isn't perfect. So this actually, I think this is compelling because it's generally slightly asymmetrical, right? You can kind of tell that something's made this, but not perfectly. So that's what makes it look alive, or like something made by an agent, right? If I just showed you the mathematical solution corresponding to this frequency, it would just look like a checkerboard pattern, more or less, and it wouldn't be interesting, or it wouldn't be as interesting. So physical patterns are characterized by a level of imperfection, and there are characteristic defects, like for example this level crossing avoidance and stuff, which have physics behind them, and we kind of intuitively like things that are a little bit handmade looking, or made by. Yeah, interesting.
We welcome a thought about this, just as someone who grew up myself being a musician in the Western domain, getting really used to like how a piano would sound and that sort of thing. I found other systems that I experienced, like court music in Japan, really weird at first, but when I played it a lot, and I did, it just became normal. And so when I pick up these different instruments in different contexts, I have an expectation that I've developed. It feels good, and I want to hear certain things in that context that do it, make me feel good, whether it's a chord at a certain point.
So a certain amount of training is involved.
And even within cultures, even within a country like Japan, it's not about like the culture as a whole. Very few people in that particular culture know that music, and so most people feel it's kind of weird, except for people who do it a lot. And that, or maybe any place, has a lot of different musics going on, and I think different groups of people have different perceptions of the same culture, right? For what it's worth, which is my opinion.
Way at the back.
I think that just to add to that, I think it's sort of maybe similar or analogous to dialect, perhaps.
Right. Yeah.
I mentioned earlier about the Cymatics, that is the fellow that's in Northern England.
Okay.
Cimascope.
Yes, I was going to build a Cimascope for this, but I didn't quite get it together.
Yeah.
It's sometimes called a cymatic tonoscope, and it's the thing that I have a picture of it. A picture's made with it right here. This is made with a device like that, and basically it's a plate with a liquid in it which is shaken, which is then projected by a light from below. And you really want to make one and look at it because it's very hard to make a video of what it's doing. It's very hard to look at it on YouTube even. And the reason is that it's actually shaking at the frequency you're shaking it at, or half that frequency if it's a Faraday wave. And that's very close to the video frame rate, and so you can't really take a video of it very nicely. So, yeah, they're easy to make.
Well, it seems like one of the things they're applying the Cimascope to is to dolphins and their communication through sonar, and they're able to, with this Cimascope, actually create a visual image of the sound.
Yes, you can think of it as a kind of transducer that takes arbitrary sounds and turns them into some picture that you can then, understand with your eye. What we would call scientifically, we would call the transfer function is what kind of sound, what kind of picture is produced by what kind of sound. It's pretty complex, and it's filtered through the nonlinear wave interactions of the fluid, and that depends in an interesting way on the fluid dynamics of the fluid. So there's actually a whole mathematical science of the modes of shaking drops and fluids and all this stuff, which the people who make cymatic devices don't know or don't care about. Jenny himself, or Jenny, was kind of obsessed with what happens when you take vowel sounds or sounds like om or things like this and play them into the tonoscope and produce pictures like this. So if I go and I get a beautiful mandala out like that, then that speaks to you, right? Now, scientifically, I can explain that, but maybe the scientific explanation doesn't speak in the same way unless you know the mathematics.
Stephen?
Yeah.
Could I ask you a question? One of the more interesting things we did in the physics lab when I was studying, Dr. Rossing would show the different modes of vibration of a timpani head.
Yeah, sure.
And he would drive that head by putting a little straw with a frequency driven into it at different modes. And then with a black strobe light, he would time it out so that you saw it in slow motion. So he would do the first mode, and it was very trippy. It's going up and down, and then he would double it, go up an octave, and the head would go like this, double, and then it would do in quadrants, and then there's circular modes as well, so that it would go like this, depending on what frequency he was driving that.
They're
was
quite
really
similar
cool.
to Chladni modes for a circular plate. They're not exactly the same because the boundary edge is a little different. But yeah, strobe light is a great thing. You can really trip yourself out.
He did that with tam-tams too, because there's like
and what's a
100.
tam-tam exactly?
It's a gong without a button in the middle.
Oh, okay.
So it has a lot of frequencies going on, non-harmonic, and he would drive that, and you would see all the different ways that it broke up into patterns. Really fascinating.
And there's lots of nonlinear stuff going on there too. If you can see the deflection, then it's not linear, right? I mean, the bigger the deflection of the thing, the more it's going to involve the stretching mode. So if I take a string and I do the simplest possible thing, I pluck it and I do the theory of the deflection of the string, what I'm ignoring is the fact that when the string goes like that, it actually has to stretch. Okay, so there's actually a second physical mode, which is that the string is lengthened by plucking, and not only deflected. And that stretching actually feeds energy into the transverse mode. So when you pluck a string vertically and you watch it, it'll go bzzz, and then it'll turn over and go into the horizontal mode like this. And those are the nonlinear modes talking to each other. And so if you have a drum head and you bash it, then all the modes that have any overlap with the one that you've selected will be nonlinearly excited. And so the whole sequence of how the thing rings down and what it sounds like doesn't just involve the linear motion of the head. It involves all that stuff. And musicians know that if you hit it harder, it makes a different sound, and if you hit it in a different place, it makes a different sound.
Sticks.
And what kind of stick you use, and all these things. But these are all missing from the simple linear theory that I was alluding to Rayleigh's picture of the thing. Yeah.
I have a question about in concert halls, problems that tuning a PA involves. So to eliminate things like, I don't know what they'd be, standing waves or something.
Yeah.
Sounds jump out, it seems to really...
Yeah. You have to be a pretty low note to resonate a concert hall, but yeah, you can do it.
Are you aware of how easy that is or how difficult it is these days compared to how it used to be?
Well, you can buy a device that sets off a little firecracker noise and measures the echo and tells you everything you want to know about your concert hall. It's a yes, it's basic linear acoustics. Yeah. The tough part comes in when you have to decide what kind of music you want to listen to in your concert hall and which one sounds better and all those kind of things. Those are not physics questions. The biggest question in a hall is your ear hears my voice coming to you directly, but then a very short time later it hears the reflection of my voice coming from the side walls and stuff. And psychologically, you tune out the reflections of the room. If we were outside, it would sound quite different because those reflections are not there. So the trick in a concert hall is to damp the reflections, and so that's why concert halls usually have sound absorbers around the back sides of them and sound reflectors around the front, sometimes reflectors up here. Because if that delay gets too long, then you have a hard time pulling it apart again. So there's a lot of psychology involved in your perception of the sound in a hall-like environment. That's why it sounds so good when you're singing in the shower too, because you're standing in a resonant cavity, which is small enough to resonate with your low singing voice, right?
I just know I sing in the shower.
Yeah.
This is a very quick basic question. This is what you guys were just talking about. So, theoretically, for a circular uniform membrane,
yeah.
So you have your radiosymmetric modes. That's fine.
Yeah.
But for the non-radiosymmetric modes, like the ones like
yeah.
What that angle? What did
it's completely degenerate in a perfect mode, and that means that mathematically that it's completely independent of the angle where you would put that node line. So the simplest non-symmetric mode is this goes up and that goes down, and you can imagine a circle. So here's a drum head, here's a node line, and this is a mode. Right? Now you're asking where does that line go, and the answer is at a perfect drum head it goes any angle. Okay? So it's we call it degenerate.
That's the 1-1 mode?
Yeah. So
there's a node where it's attached to the bowl, and then there's a node in the middle.
You can also have the middle go up and outside.
Right.
Yeah. So you can have a mode like this.
Right.
With plus here and minus here.
That would be the 2-1 mode.
2-1. Yeah. But the answer to your question is that mathematically they're absolutely exactly equivalent, and there's no physics in what angle it comes up.
It's completely arbitrary.
Correct.
The physical one will be determined just by the physical properties.
If I hit the drum with my stick here, then I'll get that one. If I hit it here, I'll get the one with the line across the middle or something like that. And if the drum head is very slightly asymmetrical, then what may happen is that there'll be two modes, which would be all the modes are degenerate, but there'll be two perpendicular modes, one of which is very tiny bit of frequency different than the other. And this one will ring, and it'll non-linearly drive that one, and you'll get a little whoa, 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 whoa as they go back and forth. And you hear this in your xylophone keys and things like that, right? Mm. I noticed that if you look at the backs of the tubes there, there's a little scratching there. So what is that?
I was trying to tune the modes that were perpendicular so that they were more in line with each other, so there was no beating.
I see.
And that's kind of tricky.
Well, that's exactly what Rob was just saying.
Yeah. Mm-hmm.
In a perfectly symmetric tube, this mode and the mode at 45 degrees to that with the nodes in a different place would be symmetrical, but in a real tube, they're not. So people who make xylophones and so on, you look on the underside of the keys, there are all sorts of little drill holes and jazz that goes on there. And I'll bet you they use electronics to tune them now.
That was what I started doing when I started my company. We tune the bars to the harmonics that we want to hear, not all of the harmonics. So the first overtone in a marimba bar is the double octave. And there's nothing.
Double octave?
Yeah.
Okay.
There's no octave, there's no fifth. It goes right up to that. And the resonators, since they're closed off, they do the odd number harmonics. They resonate. So they're only resonating they're not, in a xylophone, you tune the first overtone to the fifth. The resonator does resonate in the xylophone, the first overtone, but not on a marimba. So there's some interesting.
And that's done just by shaping the bar carefully so that it.
Yeah, exactly.
Super quick one. So the fact that you can solve for all the patterns on the cladding plate, kind of take the art out of it. Like I can mathematically solve all.
No, there's an art to solving it too.
I know that you use some variables like the plate size and maybe how perfect it is, how imperfect it is. But that's like those are the only variables.
The variables.
Well, you see, that's a forgive me, but that's a value judgment. I find the mathematics beautiful too.
I want to make say want to be a new artist, generate new amazing patterns.
Mm-hmm.
They've all been solved.
Well, what you can do now, which you couldn't do in Rayleigh's time, is that you can use a computer to solve these equations for you. And there's actually a guy who I wish he was here. I invited him, but I guess he didn't get the message. But there's a guy in the computer science department named David Levin, and he does exactly that. He takes weirdly shaped plates, cut out the shape of a teapot, right? As computer graphics people love pictures of teapots, and then he calculates the sound modes of that thing, and then he uses an algorithm to adjust the shape of the teapot and the thickness of the plate in different places to tune just as you do your pipes. He tunes arbitrary weird shapes, and then he has this xylophone, which is, I guess means it for a kid's toy, but it's a bunch of animal shapes, and if you bong them, they make beautiful chords. All the key resonances when you hit them in the center are tuned so that they're in nice ratios and they sound nice. And he's got a highly technical method of first calculating the modes of the plate, which is very complex, and then you closing the loop and moving the modes around by changing the shape of and thickness of the plate until it comes into some nice ratios that he wants. And then they go off and fabricate the plates with computer machining. So you don't need to solve the equation. What Rayleigh did is technically complex, but a computer can do that now. So you as an artist could, in reality, you could, mold statuary and bong them and listen to their noises and tell them to, you could do all this. You don't have to solve the equations. Behind it all is the equations, but in a sense, that technical step is not essential anymore. You can solve those for you. Siri, I have a teapot-shaped plate. What shape should I make it so that it rings a perfect fifth when I bonk it in this plate? Oh, I'll get back to you on that, Steve. Seriously. David Levin is his name, and he's got a couple of amazing videos. He also does this for horns. He has something called the hippophone, which is a toy, and it's shaped like a toy, like a bulbous hippo-shaped plastic thing with a horn sticking out of his mouth. And you play it, and you touch the buttons on it, touch the holes on it, and it's all tuned to make a nice trumpety sort of noise. How does he do that? Well, he calculates what shape to make the inside to get the right modes, and you close this loop of the computational loop of calculating the modes and adjusting the shape and calculating the modes and going around until you get a well-tuned hippo. And they do this. And then you make it all with a 3D printer because the shape's complicated at the end. Interesting. So, you could do that for pipes. But in practice, you'd have to computerize the making of the pipes in order to get the shape exact enough to be tuned out of the box, right? Right. It's much easier to make a pipe and then, hit it and measure the frequencies electronically and then scratch it or do whatever you do to tune. Operationally, that's much simpler than getting a computer to do it, but the computer can do it.
Could you quickly explain what happens when you hit a cymbal, put it in a pail of water, and the fish goes down instead of up?
A cymbal.
Yeah.
A gong. And the pitch goes down.
Ooh.
Oh, I know what you mean. Well, I think that's the frequency shift due to damping. If you take any resonator, it has a response function that looks sort of like this, right? And that's the resonant frequency. But the width of it is related to how fast it damps down. And if you increase the damping, very generally the peak shifts to lower frequency. So I suspect that that's what that is. Yeah. A better one is if you put hot chocolate in a glass and you pour boiling water in it, and then you stir it with a spoon, the pitch of the tapping noise goes up. You ever heard that one before? Oh, try it. It's amazing. You can find million-mile-long threads on that about people argue what caused that.
I want to thank you all very much. This is also coming from, dare I say it out loud, a piano tuner. Met with discussions about tuning modes and temperaments and such like that. But I find the discussion is just, it's never ending, but I feel like music and percussion and tuning has happened, I think, much longer than we have been able to understand the math behind it. I wish I could understand the math behind it. I was terrible at math and science, but I've always appreciated the beauty and appeal and the sort of artistic expression of it. But I'm starting to think now about tuning, the different tuning modes, almost as being like a different color, as if maybe, say, the type of music you would hear and the tuning modes you'd hear, say, in Indonesia, that music would sound good with, say, a purple temperament. But if you put
That's a very synesthetic thing to say. There's a thing called synesthesia, which connects things like colors and sounds, yes.
But I did a gamelan course in university, and I remember noticing that everything was kind of out of tune, so to speak, all these beats and the shimmering. But my instructor said that that was actually on purpose because the aesthetic was this sort of shimmering, almost like a gold. Because the instrument is, I think, is it brass? The piece is bronze. Anyways, it's gold looking, and the painting on the gamelan is very bright red and blue and very sort of festive looking. And she said, well, they're not supposed to be perfectly in tune because that sort of shimmery sound and this sort of gold, shimmering, beautiful aesthetic. I thought, well, there you go. It's supposed to be this way. It's not like.
And it's something Stephen said earlier. It's really subjective. We often view things from our culture, right? And so to say gamelan music is out of tune, it's not to them. It's like really in tune to them, and they think we're out of tune. And we went to, I think you were there, Russell. It was in Austria to hear the Vienna Philharmonic play, and you were with Abraham Xenia, an African drummer, and I may have mixed up the names, but they took him to see a classical concert, and afterwards they said, what did you think of that concert? He said, it was really beautiful, but why did they play the same piece over and over again? So it's really, from our perspective, and what's happening with that phenomenon you were talking about with the gamelan is really interesting because in the larger gamelans, there's pairs of players. So there's two instruments that play the same part in unison, right? And very complicated rhythms and all that, but the bars are detuned by 7 cents or 7% difference, so that when you hit the two notes together, it beats at that rate, ba wah 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 wah. And they do that throughout the whole ensemble, from the lowest instrument to the highest instrument. So it puts a lot of people in work, which is great because you have to have two players to play one simple part, and then you have two players playing the counterpoint, the hocket, they call it kotekan, so that you get the shimmering between the two pairs. And it's really phenomenal. And I hear people call it primitive. I mean, it's so advanced and complicated. It's just amazing.
And then after the gamelan course, I started learning folk singing from the Republic of Georgia, where they sing normally with neutral thirds, but of course we could not quite grasp neutral thirds to try and recreate them very accurately. Quite excited about words, parallel stacked fifths.
Getting too technical for me.
Parallel fifths is like they stack them in parallel.
Yeah. Well, don't get me started on throat singing. Throat singing.
Oh wow, that's just a whole other.
So what's fascinating is that people independently, through some kind of cultural process which isn't scientific, arrive at these amazing things, and you kind of come back to them and you can kind of take them apart, but. And nobody ever made the gamelans by thinking, I need a mode that's a little different than this one, and so what could you do if you went the other way? It's not something that people do normally. Yeah.
I was going to ask that same thing. If you've experienced in either of your fields other examples of that phenomenon something being discovered, whether on either sides of an ocean, or I know, for example, that like photography was discovered at a very similar time in two completely different countries in Europe. People came to the same conclusions, but there was the daguerreotype and another type of photography. But two different conclusions found similar fashions, but slightly different, almost at the same time in history, but irrespective of each other. Have you noticed that?
Oh, things that are discovered simultaneously all the time in science.
Airplanes.
As soon as the time has come for something, it comes, and whoever finds it, it's just the first one to get there. And it just happens all the time in science. There's just simultaneously discoveries going on all the time. What's interesting about Jenny is that he's 150 years displaced from Faraday, and almost unaware of that disconnect. But both of them, in some ways, motivated by the same phenomenon and making the same pictures, and even discovering the same, odd things like the cornstarch monster.
It's not only a human phenomenon. For example, winged flight in mammals.
Yes, that's right. That's right. We explore the range of possibilities and we find everything, or almost everything. Yes, we have to be out here. We want to make three announcements. This is an ArtSci Salon. If you like the collision between art and science, please join our mailing list. Or Roberta's already got ya. We have an event a few times, sometimes as much as once a month, and usually a few times a term. And it's here at the Fields Institute, organized by Roberta. This is actually one of a series of several events in the Jackman Institute series, and there's another group of things tomorrow starting at noon, and there's two more lectures at 4 and 5 tomorrow in the music building, and then there's a performance on Friday.
Yeah, lectures are
3 and 4.
Hey.
No demonstrations.
I won't ruin your instruments. That's
all right.
I promise. Can we mention, and I will because I'm going to now, Saturday at the Music Gallery, what time are we? Nexus is playing music of Moondog at Russell Range.
Yeah, so if you're interested in this obscure but very interesting composer, sort of pre-minimalist, who's friends with Steve Reich and Philip Glass, and members of the New York Philharmonic. So there's a special concert of some of his music, arranged specifically his music at the Music Gallery.